Number 41. Plutonium was detected in trace amounts in natural uranium deposits by Glenn Seaborg and his associates in 1941. So that was what, 80 years ago? Every time I look at 1941, I'm always like, oh, that was 60 years ago, because my brain is somehow still trapped in the 2000s. But we are now in 2023. So this was actually 80 years ago. That's nuts. But anyway, Glenn Seaborg and his associates, they proposed that the source of this plutonium-239 was the capture of neutrons by uranium-238 nuclei. Why is this plutonium not likely to have been trapped at the time the solar system formed 4.7 times 10 to the 9th years ago? Okay. So, long story short, right, Glenn Seaborg and his associates, right, they found trace amounts of plutonium in some natural uranium deposits. So they maybe hypothesized that this plutonium was actually around when the solar system, came about, right? When the solar system formed 4.7 times 10 to the 9th years ago. But now we propose the question and say, why is that not likely, right? Why is that not likely that the plutonium that Glenn saw was not around when the solar system formed? Well, in order to answer this question, we had to get some extra information. Now, we did have to get the half-life, and that's what this T-half is. This T-half means the half-life. Can't find this question out or can't answer the question out without that half-life information. Now, plutonium's 239 specifically, because that's what we're talking about, plutonium's half-life is 2.4 times 10 to the 4th years. That means every roughly 24,100 years, a sample of plutonium will split in half, right? 50-50. And then it will degrade, by half again and by half again. And that happens, cutting off half is going to happen every 24,100 years, or 2.41 times 10 to the 4th years. So now, we have to say why that plutonium was not around when the solar system formed. Well, if we wanted to find out, we can use our radioactive decay formulas, right? Now, just know that any radioactive decay, I don't care what element you're talking about. You want to talk about uranium? Sure. You want to talk about plutonium decaying, carbon-14, whatever you want to talk about, this is always first-order kinetics. And chances are that if you are doing your nuclear chemistry chapter, you probably have already done your kinetics chapter. Oh, and if you've done your kinetics chapter, you've already learned your first order kinetics equations. With a new formula, a lot of teachers or professors, they give you a new formula or two new formulas to memorize. But I don't say let's do that, because it's always going to go back to the formulas that you know. You already know your first order kinetics equations if you did the chapter, so we could just use those. Now, in this case, they're giving us an arbitrary amount of time. The solar system formed 4.7 times 10 to the 9th years ago. That has nothing to do with the half-life of plutonium. So this value is how long we got to go back. So this is just going to be our random t value, 4.7 times 10 to the 9th years. And if we are using our first order kinetics equations and we just have a t value, we're going to be using this formula. But now the question is, what are we basically trying to solve for here? Well, we want to know how much, right, in theory, right, how much plutonium should we still have after this amount of time, given its half-life? Now, let's start with that, right? Now, the amounts, whether you're going to talk about grams or fractions or percents, right, your amounts are always going to be these bracketed A's. And the 0 one indicates that 0 time has passed. So your initial amount, let's search for it. Now, in this case, they didn't tell me how much plutonium was initially there. So I can't really use grams, I can't really use molarities or moles. So we could use other units such as a fraction or a percent. Me personally, I'm always going for percents because they're easier for me. But if you want to use fractions, that's fine as well. I know that in the beginning, any initial percentage, right, is always what number? What is the highest percentage possible, right, out of, a substance? Yeah, you got it. It's 100%. Right? When you order a pizza and you open up the pizza pie, I hope that 50% of the pizza's, only there, right? I hope not. Then I'd be calling up the pizza place. You want to make sure that when you open that pizza pie, you get 100% of that product. So the 8 slices. The same thing here. Here would be an initial of 100%. Now, well, we're going to find out how much is left after the 4.7 times 10 to the 9th years has gone by. So you start with 100. 4.7 times 10 to the 9th years, that's going to be the t-value, has gone by. We want to find out the final amount. Right? If we have so maybe I'll just say X, right? If we have 10% left, well, yeah, then maybe that plutonium, is going to be the plutonium that Glenn saw. But if we get a really, 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 really small number, like close to 0, right? Then that means that chances are that plutonium was not from that amount of time. The 0 value, if we do find out, it being close to 0, the 0 means that after this amount of time, the plutonium would have been all gone. There would have been none left. Because you're always finding out the final amount that's remaining, not how much that's gone. Okay. Now, the only other piece of the puzzle here is I need to find out that K value. And the K value is the rate constant. But in the question, they didn't tell me what the rate constant of plutonium was. Now, keep in mind, we don't care about the uranium because that's not the radioactive substance that we're talking about here. They keep asking, why is this plutonium not likely to be abstracted? So all of your values and your substances here can only be for plutonium. But they didn't give me a rate constant for plutonium. But that's where the other first order kinetics equation comes in. And that's why we needed that half-life. Because without that half-life, we couldn't have found the K value. And because of that, we couldn't have plopped it into this formula to solve for what we wanted. So let's just go a little bit off course here. We know that the half-life, by looking it up, by me looking it up, before the start of this problem, we know that it takes 2.41 times 10 to the 4th years to decompose the plutonium into, 50%. So if I just say, and maybe I'll get rid of the units here, because usually when I do my math, I don't like units. I just tack them on at the end. So this equals 0.693. I'm going to solve for K. What you can do is cross multiply, which is what I'll do. So this, times this, and we get 2.41 times 10 to the 4th times K equals 0.693. We're going to solve for the K value. So we want to divide by 2.41 times 10 to the 4th on both sides. This gets bye-byes. Can I move this up a little bit? Yes, I can. I'm like the little engine that could. The coffee is great. Okay, K equals 0.693 divided by 2.41 times 10 to the 4th. Just making sure that I plugged in the right numbers. 2.41, that looks good to me. To the 4th point, there we go. Okay. So we're just going to round it a little bit here, but I'll use the full number for my calculation to 2.8755 times 10 to the negative 5th. And since the half-life was in years, this is going to be per year, so years to the minus 1. Now I have that value. This K value is 2.8755 times 10 to the negative fifth. And now, let's use this formula to solve for how much should be left after the random solar system amount of time, 4.7 times 10 to the ninth. So let's go. ln, I'm just going to lay out the framework here. We got negative kt plus ln. Okay, so we got ln of x, and the blue is 4.7 times 10 to the ninth. We got 100 for this guy, and then we got 2.8755 times 10 to the negative fifth. Okay, so actually what we can do is we could plug this all into the calc at once, but if you want to do this section first, get that number, this section, and then add the two together, go for it. I'm just going to plug it all into calc at once, so ln of x equals, that's why I love the TI 84. It's a beautiful thing. This times 4.7 times 10 to the ninth. Then we're going to plus the ln of 100. Yeah, that looks good to me. Oh boy. It's really small number. So small that I don't even think we're going to get a value for the next part, but that's why this is not likely, as per what we said a little bit time ago. But if we want to get rid of the natural log, e is the inverse. So essentially we'll do e raised to this. This gets canceled out, and we have x equal to, right? This is the final amount that's remaining. So drum roll, please. This is what we've been waiting for. E raised to this value. There we go. Boom. So this means that we have, at the end of the day, 0% remaining. So, why is this plutonium not likely to have been trapped at the time the solar system formed, 4.7 times 10 to the ninth years ago? It is because with plutonium's known half-life, it would have run through so many half-lives in which once the 4.7 times 10 to the ninth years has gone by, right, the plutonium would have decayed and there is 0 remaining. And that, my friends, is the final answer. So we will have 0% remaining at the end of the day, so you wouldn't even see the plutonium because it all has decayed into something else. I hope this helped. Thank you so much for viewing the video. I love helping you guys. I love doing these problems for you guys. Let me know in the comments if this helped you. We also have physics and math videos on the channel as well. So if you're in that class, if you know any friends that are in that class, we could help them as well. Thank you so much. If you want to be part of the membership, we got tons of perks for you guys. We got 4 different tiers if you want to help us out a little bit more. And yeah, as always, I hope you have a great day. Keep studying hard. I believe in you guys. And I'll talk to you soon, okay? All right. Bye-bye.